Light is the fastest thing we know. It's so fast that we measure enormous distances by how long it takes for light to travel them. In 1 year, light travels about 6 trillion miles, a distance we call 1 light year. To give you an idea of just how far this is, the moon, which took the Apollo astronauts 4 days to reach, is only 1 light second from Earth. Meanwhile, the nearest star beyond our own sun is Proxima Centauri, 4.24 light years away. Our Milky Way is on the order of 100,000 light years across. The nearest galaxy to our own, Andromeda, is about 2.5 million light years away. Space is mind-blowingly vast. But wait, how do we know how far away stars and galaxies are? After all, when we look at the sky, we have a flat, two-dimensional view. If you point your finger to one star, you can't tell how far this star is. So how do astrophysicists figure that out? For objects that are very close by, we can use a concept called trigonometric parallax. The idea is pretty simple. Let's do an experiment. Stick out your thumb and close your left eye. Now, open your left eye and close your right eye. It will look like your thumb has moved, while more distant background objects have remained in place. The same concept applies when we look at the stars. But distant stars are much, much farther away than the length of your arm, and the Earth isn't very large, so even if you had different telescopes across the equator, you'd not see much of a shift in position. Instead, we look at the change in the star's apparent location over 6 months, the halfway point of the Earth's year-long orbit around the Sun. When we measure the relative positions of the stars in summer and then again in winter, it's like looking with your other eye. Nearby stars seem to have moved against the background of the more distant stars and galaxies. But this method only works for objects no more than a few thousand light years away. Beyond our own galaxy, the distances are so great that the parallax is too small to detect, with even our most sensitive instruments. So at this point, we have to rely on a different method, using indicators we call standard candles. Standard candles are objects whose intrinsic brightness, or luminosity, we know really well. For example, if you know how bright your light bulb is, and you ask your friend to hold the light bulb and walk away from you, you know that the amount of light you receive from your friend will decrease by the distance squared. So by comparing the amount of light you receive to the intrinsic brightness of the light bulb, you can then tell how far away your friend is. In astronomy, our light bulb turns out to be a special type of star called a Cepheid variable. These stars are internally unstable, like a constantly inflating and deflating balloon. And because the expansion and contraction causes their brightness to vary, we can calculate their luminosity by measuring the period of this cycle, with more luminous stars changing more slowly. By comparing the light we observe from these stars to the intrinsic brightness we've calculated this way, we can tell how far away they are. Unfortunately, this is still not the end of the story. We can only observe individual stars up to about 40 million light years away, after which they become too blurry to resolve. But luckily, we have another type of standard candle, the famous Type 1a supernova. Supernovae, giant stellar explosions, are one of the ways that stars die. These explosions are so bright that they outshine the galaxies where they occur. So even when we can't see individual stars in a galaxy, we can still see supernovae when they happen. And Type 1a supernovae turn out to be usable as standard candles, because intrinsically bright ones fade slower than fainter ones. Through our understanding of this relationship between brightness and decline rate, we can use these supernovae to probe distances up to several billions of light years away. But why is it important to see such distant objects anyway? Well, remember how fast light travels. For example, the light emitted by the sun will take 8 minutes to reach us, which means that the light we see now is a picture of the sun 8 minutes ago. When you look at the Big Dipper, you're seeing what it looked like 80 years ago. And those smudgy galaxies? They're millions of light years away. It has taken millions of years for that light to reach us. So the universe itself is in some sense an inbuilt time machine. The further we can look back, the younger the universe we are probing. Astrophysicists try to read the history of the universe and understand how and where we come from. the universe is constantly sending us information in the form of light. All that remains is for us to decode